Okay, everyone, let's wrap up hypothesis testing. So to wrap it up, let's review once again our 4 steps. So we have the first one, state the hypothesis. We know we have 2, the HO and the H1. So HO, no difference between what you're doing and what's already been done, essentially. And H1, the alternative hypothesis, there is a significant difference between what you're doing and your results and what's already been done. And if we talk about the second one, setting our criteria, and we know our criteria specifically in hypothesis testing has to do with 3 things: our alpha level, our critical region, which is the place in the tail where we're going to find that extreme significant difference. And then we also have degrees of freedom, which doesn't apply yet for us because we're doing the one sample z-test, but will apply once we move on to the actual t-test and the other tests moving forward. And step 3, compute and analyze, in other words, run your test, and then actually think about the analysis, the results of those numbers as compared back to steps 2 and 1. And once you make that comparison back to steps 2 and 1, lead you typically to step 4, which is basically making a decision and writing it up in APA format because this is for psych stats. So once again, let's look at our normal distribution. Our normal distribution has a mean of 0, theoretically, right, and a standard deviation of 1, which means that everyone is about 1 point above and 1 point below the average. And when we actually look at this curve, remember, talk about the regions again. So if we're talking about the regions, the body, where the biggest piece would be where the 95% lies, and the tails, the smaller pieces, would be where the extreme or significant difference is. So if we look at these, let's think about, once again, if we're going to increase statistical power. If we wanted to actually run a test and say, all right, I'm going to run it at 95%. I want to be 95% sure that if the results that I'm looking at, I only have a 5% margin of error or a 5% place where I could have found significant difference. That leads us to an alpha level of 0.05, right? Which is usually the default and the most common. Now you can decide to have this 95% alpha level in 1 tail or 2 tails. In other words, a directional or non-directional test. When you actually run a test and say there is a significant difference or there is not a significant difference, but you don't specify where the difference lies, all you basically said was there is a difference. That means you led yourself to 2 places where the difference could be, on the positive end or the negative end. But what if you want to increase power and say, I want to make my test stronger because of the fact that you can actually find difference in 2 places. Making your test stronger or increasing power would actually be saying that you're going to have 1 tail. So you're going to actually decide if the difference is going to lie on the increase, better, positive end, or the lower, decrease side. The moment you decide to actually have 1 tail, you are increasing your power. Right? So increase power. My handwriting's a little off, I apologize, right? Increase power. So first, deciding if you can have more than 1, that you can have 1 tail, because having 2 tails makes your test easier. We can all see 1 tail makes it a little bit harder for you to land in 1 specific spot. You can also, besides your tails, you can also increase your alpha level. But increasing your alpha level, going from a 0.05 to a 0.10, gives you a bigger tail. Yes, but the problem is it also increases your chance of having a type 1 error. In other words, having a false positive. Because you have now 10% chance of getting into a significant difference area, as opposed to a 5% chance of getting to a significant difference area. So you can increase the power by increasing your alpha level, but you also increase your type 1 error. So in reality, you'd rather actually make your test 1-tailed than actually making it an increase in your alpha level. But that's also an option. The third thing that you could do to increase power is having larger sample sizes. Having a large sample size gives you more power over small sample sizes. And when you learn about the central limit theorem, you start to understand that sample size should be at least 30. And 30 and beyond will lead you to infinity. So 30, 40, 60, 100, 200, right? Get my drift? So being bigger than 30 or being bigger in your sample sizes also increases your power. Because we can all understand that 1 person cannot represent an entire group of people. We can when we do an average, because that means you took into account every single person's voice, and then you actually did a mathematical computation to come up with that 1 value. But just taking 1 person and saying you're going to be the representation of everyone, we know unfortunately is not valid. So in reality, getting larger samples, larger groups of people to be representative of a population makes more sense. For example, let's have a population of 10,000, and having a group of 25 people represent 10,000 probably isn't realistic. But if you have 10 groups of 25 people, or you have 10 groups of 100 people each, then we're talking 1,000, right? 10 times 100, 1,000 representing 10,000 people. That is more realistic. So to increase the power of a test, you can make your sample sizes larger. You can increase your alpha level from 5% to, let's say 10%. Or you can also decide to make it one-tailed, specifically predict where you think the difference will be, on the lower or the higher, instead of giving yourself two chances of finding a difference in two different places. Once we decide to increase our power, we can also then, once we run our actual test, think about the test itself in terms of its magnitude. Once we actually did land in a tail, in the idea of the extreme significant difference. Remember, if you're in a tail, you're extremely different. If you're in the body, in the bigger end, you are just like everyone else, which means the null hypothesis, no change, no difference between what you were doing and somebody else was doing. So in reality, if you want to then think about the magnitude and say, okay, great, I ran a test and the result of my test said I cured cancer. How effective? What's the magnitude of that cure? Is it going to help 100 people, 1,000 people, 10,000 people? Is it worth investing, or was it just a medication that helped that select group, but in reality can't be generalized? You have to measure the magnitude with which that actually result was significant to really know if you should probably invest money or you should continue with that work. So what do? We do something then called Cohen's D. Cohen's D is the measurement of testing the magnitude. And what are you doing? You're testing the difference between people who received the treatment minus those who didn't receive the treatment. So when we're looking at that difference, we're actually going to test the magnitude, the effect of a sample if it came out to be significant. And so Cohen's D essentially gives you a formula. D equals, right, the mean of the sample minus the mean of the population. Is there a difference between the sample and the population? Divided specifically just by the standard deviation, not the standard error of M, just the standard deviation, to allow you to measure the effect or the magnitude of that significant result if you did land in a tail and find a significant difference between the sample you were testing and what everyone else has done within that population.